So I'm going to go ahead and go to the next slide, but if you need more time to read it, I included a link. There's a link right there if you need to go back and actually read that document some more. But I'd like everyone to share at least one thing on this Collaborate board here about mass and weight. What's the difference? What's similar? Anything that you know about the difference between mass and weight? Go ahead and put that on the Collaborate board. So weight is caused by gravity while mass is because of matter, right? That's a good summary. Mass will determine how much inertia there is on an object good. Weight is gravity, mass is matter. That is a very succinct way of saying that. Yeah, and then there's this last one here is important, right? Mass is proportional to weight. So there is a connection, and some of the things that sometimes confuse us on this, like if you go to Europe, they don't measure weight in pounds; they measure it in kilos. But again, kilograms is not a weight; that's a mass, right? So we got to be very careful when we're talking about physics about the difference between weight, which is a force due to gravity, and mass, which is how much inertia or how much matter there is. So let's see here. Now, let me ask another question, and I'll have you put down what you think. Do you have a guess about what the units for weight are or the units for mass? I don't think it says it, but we've kind of talked about it before. Given that we know that weight is a force of gravity, what do you think the unit of weight is? And then what do you think the unit of mass is? So Gabe, yeah, kilograms for which one though? Kilograms is one of them. Yeah, kilograms for mass, I agree. So yeah, kilograms for mass. Anyone know what weight is? Weight is a force. So like other forces, weight should be measured in, okay, we could do ounces in the imperial system. So an ounce is like the feet of weight. Pounds is, well, ounces and pounds are imperial system. I would say for the metric system, newtons. So newtons is going to be the unit for weight in the metric system. Okay. All right. And again, that's because it's a force of gravity. All right. So now, here's what I want you to think about. If an astronaut travels to the moon, which is probably true, is it probably true that he has the same mass but a different weight when he goes to the moon? Do they have the same weight but a different mass? Is the mass and weight the same, or are they both different than they were on Earth? What do you think changes when you go to the moon? Mass, weight, or both, or neither? All right. Looks like I'm missing about 2 people. Go ahead and just your best guess. All right, let's see what we got here. So we tend to be favoring that the astronaut has the same mass but a different weight. That is correct. Yes, the astronaut has the same mass but different weight, because again, there's the same amount of matter. It's the same astronaut, so it's the same amount of matter, but the moon has less gravity. And so since the moon has less gravity, the weight changes. All right, we got here. Okay, now remember this equation, Fg equals mg. So we've used this equation before. Here's my thought. There's a 55 kilogram astronaut on the moon. Using that equation, Fg equals mg, what's the astronaut's weight on Earth? So again, weight means force of gravity. What's the mass on Earth? What's the weight on the moon? What's the mass on the moon? Now, one thing that I'll say here is this G equals 1.6. So G equals 1.6 on the moon. On the Earth, G equals 9.8. So, so that should help you see what you can do with these. Can't do all of them, do as many as you can. Hey, Thomas, I'm going to send you the link that you need to log into the Nearpod for today. So Thomas, it should be in your chat now. Oh, hey Gabe, so the deal is I want four different answers. One for like, what is the mass? What is the weight on Earth? What's the number? What's the mass on Earth? What's the weight on the moon? What's the mass on the moon? Now, does anyone know two of these are easy because two of them are the same? Which two are the same? I know. Feel free to say it or put it in the chat. You told me in the last slide which two you thought were the same. Yeah, the masses, 2 and 4. Max, that's right. So the masses are the same, right? So the mass should be 55 in both cases. What I'm going to say here, and I'll go ahead and share this here in a second, but the idea, right, again, weight is force of gravity. And since force of gravity is mg, on Earth, it should be whatever 55 times 9.8 is. And on the moon, it should be whatever 55 times 1.6 is. And Gabe, looks like you got it. Yeah, Stephen, you've got it. Chloe, you got it. Camille, I think you were dividing instead of multiplying. So I'm going to just put this in and I'm going to share it. Share it with everyone here so that you can see it. So this is how I would do it, right? So on the Earth, mass times 9.8, mass is 55. And on the moon, it's going to be mass times 1.6, right? Questions? Anyone got any questions before I go on? All right, let's go on. Okay, now, so that's the idea of the difference between mass and weight. Now, here's a question about how do we feel our weight? So I want you to think about in an elevator. There are probably times in the elevator when you, at least momentarily, feel a little bit heavier than normal, like at least for a moment. Or there are times where like you feel lighter, you kind of feel like your stomach kind of like comes up a little bit, right? So I want you to think about when is a time, so we'll do another one of these collaborate boards here. Think about a time when on the elevator, what's the elevator doing when you feel heavier, when you do lighter? There's more than one answer. But when do you feel heavier, at least for a split second on the elevator? When do you feel lighter? We got when it's moving up. I want to say a little bit more about when it's moving up. What time? Because I don't think you feel different the whole time. So when I go up and there's a sudden stop, right? So we've got the sudden stop or, yeah. And then there's a lighter when you're going down, and when it's moving down, it's not the whole time, right? It's at the very beginning. You get to a stop and it moves up. Yes. Lighter feeling down, heavier moving up. It's going up. Yeah, but the key is, right, it's when the acceleration happens. So while you're moving up or while you're moving down at a constant speed, I don't think you feel it. But you do at the beginning and the end, right? When it's either when it's just starting or when it's just stopping, you've got that acceleration. And that causes you to feel a little bit different, right? Now we could explain that using the first law, the idea of inertia, but I want to think about it a different way. So here, what I'm going to ask you to do is, we're just going to imagine first of all that you're the elevator is not moving. So I want you to draw a free body diagram. So you're the best that you can with a mouse. All the arrows, and what I'm really interested in is I'm interested in like which arrow's bigger and what you would like forces. So you should be able to draw just by using your mouse, and you can also insert text if you want to label your forces. So go ahead and draw a free body diagram if the elevator is just at rest. Hi Lee, I'm going to, I'm sending you the link to log into our Nearpod. So it looks like we're all getting, we definitely have the two forces. Now I want to, if I could real quick, and I know some of you are still drawing, but I want to say something about a couple of these. So real quick. I think that we have to have a situation in which the net force is 0, right? If you're stationary, the net force has to be 0. And then we have a question about what we're going to call it. So so here's one example. No, why can't I share that one? Trying to get one that's almost right, but not quite right. This one's the one I want to share, but I can't. It's not submitted. Oh well. So here's the deal, right? You got the best example, I'm going to go ahead and just share this one because I think this is the best example, right? So the key is you have to have a net force of 0, and you've got normal going up and you got gravity going down. Now, some people put tension going up. So I guess what I got to be clear about is, am I drawing the free body diagram for the person or for the elevator? If you're drawing the free body diagram for the elevator, then it is tension that's going up. But I want to focus on the person. And maybe I didn't make that clear. But if I'm focusing on the person is not being held up by a rope, right? The person's not hanging, right? It's the floor of the elevator that's pushing on them. So I'm going to say that this is what we want if I'm stationary. We want the net force to be 0, and we want normal to point up, gravity to point down. That's what's happening if you're stationary. Now, I'm going to ask you with that in mind, again, so the two forces are normal and gravity. So call the upward force normal instead of tension. Call the downward force gravity. If that's the case, how does this free body diagram change if you start to accelerate upward? So redraw this free body diagram. Again, the two forces are gravity and normal. But how does it change if you're accelerating upward? Yeah, so and most people I'm seeing are doing they're doing the size of the arrows right, but again, I want to call the upward force normal. So if you've called it tension, again, if you called it tension, you're drawing a free body diagram for the elevator. I want a free body diagram for the person. And so if you've submitted it and you have tension going up, change that to normal as the upward force. So yeah, I'm gonna go ahead and share this one. So yeah, the key is up has to win if you're accelerating up, and the normal force is bigger. Now think about that. When you're accelerating up, so you get in the elevator and it starts going up, so you're accelerating up, is that a time of feeling heavier or lighter? I think that's a time of feeling heavier, right? So here's what I'm gonna say. You don't know how, it's not your weight that tells you, like, that helps you sense how heavy you are. It's the normal force that tells you how heavy you are, right? Usually when we're either in a stationary elevator or we're just staying put on a stationary ground, right? Usually normal force and gravity are equal. And so we feel as much normal force as our weight. However, if you're accelerating up, you need more normal force, and so you feel heavier. So what I'm going to say is how heavy you feel is not due to your actual gravity. How heavy you feel is due to the normal force. With that in mind, I want to do one more of these drawings. So what if we're accelerating down? And just to share with you here so that you can refer to it, right? I've included the free body diagram for the upward accelerating elevator. So normal is bigger than gravity. Now I want you to do the free body diagram for the downward accelerating elevator. right. So I'm going to share one. I really like this drawing because you can tell that the gravity is the same, right? Because your actual weight, your actual force of gravity didn't change, right? So your weight is the same. It's the downward arrow is the same size as it was over here. What's different is the upward arrow, right? So now that you have less normal force, you feel lighter. The only thing we could do to add to this picture is make sure to include the net force as well. Yeah, but the idea is if you're accelerating down, you have less normal force than gravity, and so you feel lighter. So how do you think you'd feel weightless? Anyone want to take a stab at that? Anyone know how you feel weightless? What force do you need to get rid of to feel weightless? Any thoughts? Well, that would be one way to do it, is to get rid of gravity. However, again, it's not gravity that tells us how much we weigh, right? Because that person that's in a downward going elevator still has the same amount of gravity, but feels less, right? I need to get rid of, yes, Max, I need to get rid of the upward force. I need to get rid of normal. So if you've ever been to like Drop Zone or Tower of Terror or any of those rides where they put you in a car and then they just drop you, right? And you feel weightless, like that is what weightlessness feels like, right? Because weightlessness, again, we don't know that we're weightless because we don't have weight. We know that we're weightless because we don't have a normal force. That's how we feel weightlessness, right? So the other thing is, you imagine how that free fall feels if you ride one of those rides. That's how astronauts in the space station feel all the time, right? Because they essentially feel like they're falling all the time. All right. The last thing that I've got before we leave here is just some check for understanding. It's about stuff we've talked about today and all of e-learning. There are 8 problems. You're not gonna lose any points if you get any wrong, but I just want to, but try your best. I want to see how we're doing on it. It was terrifying. What, Tower of Terror, Chloe, or e-learning? By the way, yeah, if you guys could answer the Tower of Terror. Yes, I hate it. I can't stand Tower of Terror. Because the other thing is, it's not like it just drops you. Then it just keeps going up and down. So once you've answered the 8 questions, again, try your best on the 8 questions. And then once you've answered them, you are done for the day.